questions for the presenters that are presented or provided to us beforehand for the webinar, and we'll start with these. But this is also an opportunity for our participants here. If you can think of questions, just type those in and get those to us, and we can get our presenters to address those questions for you. So at this point, to go ahead and get things rolling, I'm going to start with a question, and this one is going to be directed to Larissa Golovko. And the question has come in earlier from Edwin Munitz from the U.S. Department of Agricultural Natural Resource Conservation Service. And Edwin's question for Larissa is as follows. What is the possibility of using electrical conductivity or electrical resistance to map heavy metal concentrations in the soils? Yes, Larissa, would you like to maybe say a little bit about what your thoughts are on this?
Okay. Well, depending on the metal and the concentration of the heavy metal, like heavy metal pollution is usually they kind of bind to soil, so they're not mobile. So conceptually, they are not influencing EC enough. But on the like we've done some preliminary research, there are remediation techniques when the solutions are kind of leach through soil and they bond to those metals and they became mobile. Then you can monitor the process of, you know, kind of cleaning the soil. When using the leaching, or there was project on bioremediation when the plants were uptaking those heavy metals from soil. That's all I have to say. Anybody else can?
Yeah, thanks, Larissa. Yeah, does any of other presenters want to add something on this particular question?
Hello, Barry. It's Rick here. Can everyone hear me? Barry?
Rick, this is Stephen jumping in. You're really quiet. Could you please speak up when you're answering the questions? Thanks.
Okay, sure. No problem at all. Since the 1980s, ECA has been used to outline contaminant plumes. Now, specifically with heavy metals, the heavy metals probably got into the soil through insolution in salts and acids. While we wouldn't be mapping any ECA effect of the metals because they're not joined up, they don't really enhance the current flow too much. What we can do is map the salts and acids, the dissolved solids that have invaded the pore spaces and in some cases, bound themselves to clay particles, which would increase the conductivity.
Thank you, Rick. So anybody else like to kind of add some insight on this? If not, maybe go on to our next question. And this question is really going to, I think, it's an interesting one. I think it's going to be addressed to all of our presenters. And maybe if you may or may want to take a chance to take a stab at this. This question is from Paul Howell, again with the U.S. Department of Agriculture, Natural Resources Conservation Service. And Paul's question is, how can shallow, and in this case shallow 10 to 30 feet deep, subsurface leakage flow paths in limestone bedrock and leaky embankment ponds be located? The flow paths are usually in the abutments or base of the abutments. So does anybody have some just off the top of your head, some ideas on how you might use geophysics to address the problem that Paul has brought up? And maybe I'll just start, kind of go down the list. Maybe Jim, do you have any idea on this? And if not, maybe we'll go on to Slava and just see what you all think.
Well, Barry, I think Paul is probably talking about agricultural waste, and there's been a lot of research on using electromagnetic induction to measure contaminant plumes. The problem is getting the right meter or sensor to measure the depth and give the resolution that's needed. But I've done some work in limestone areas, but looking for karst features, but never contaminants running through them. Maybe Rick would have something to say on this as well.
Oh, Rick, do you have anything that you'd like to mention?
Yeah, sure. Now, karst features are difficult to really characterize with EMI unless they have some sort of conductive filling. Even if you have a fraction that contains conductive fluid, that fraction can provide a good response because to develop a pretty big surface area with conductivity that will really let current flow get going. So the key is what inhabits the fractures and structural features of the limestone. If it is conductive pore fluid, yeah, EMI, not the short arrays that we tend to see with soil mapping, but arrays of separate transmitters and receivers held about 10 meters apart would be the tool to use.
Thanks, Rick. Larissa, if you're there, I might check with you. I've done maybe seen some literature where self-potential methods have been used to detect leaks from, say, landfills and treatment ponds or things like that. Do you think self-potential methods would have a potential application here for isolating, leaks through the embankments or through the limestone?
Yeah, actually, one of the earliest application of self-potential was detecting where is the leakage from the dams. I think it was like in 60s or even 40s. In England, there was publications on that. So basically, in anywhere there's a water flow, water flux, and water is moving, especially if there is soluble salts in there, you can pinpoint the areas. But the thing is, if we want to monitor like how much is going in and out, then you might look into more like quantifying methods like electrical tomography, for example, like resistivity tomography with right spacing, and you can go as detailed as you want.
If I remember correctly, I think that Roger Eigenberg at Nebraska has been looking at using geophysical methods for monitoring leakage from animal waste storage lagoons and things like that.
Yeah, he actually used tomography, electrical tomography, and there is 2D software just going like every week, if it's correct, but comparing the pictures like before and after. It was pretty accurate in a sense.
No, Slava, did you have anything you want to add on this, or we want to go to the next question?
one thing that relates to some work that Roger did was not only looking at the map of how electroconductivity changes, but actually looking at the ratio at some of other parameters, because if you have material, like organic material from other with different features coming in, then there is a tendency that it would accumulate within a certain layer of profile, and then looking at some indices might help allocate those areas.
Thank you, Slava. Okay, go on to maybe a next question, and this one is going to be directed to Rick Taylor. And Rick, EMI methods can provide measurements of soil electrical conductivity, but also soil magnetic susceptibility. Could you maybe explain to our audience a little bit of what magnetic susceptibility is? And could soil magnetic susceptibility measurements using EMI methods maybe have any use for agriculture?
Yeah, okay, thanks, Barry. Magnetic susceptibility is a measure of how easily a soil can be magnetized. If you have an external magnetic field, you expose the soil to that, you measure how much more magnetism you get that aligns itself with that external field. Soils have varying susceptibility, primarily on the basis of how much magnetite they contain, but also there are other iron minerals and organic processes that develop magnetizable materials in the soil. But I don't think that magnetite content or susceptibility is really generally related to either agricultural productivity of the soil or erodibility. And also the things that we tend to want to measure in precision agriculture, moisture, dissolved solids, wastes, they really tend not to have much susceptibility contrast either to the soil. The other complication is that susceptibility shows up in not the component of response that's proportional to electrical conductivity, but it shows up in the component of response that's in phase with the transmitted field. So it's more difficult to get an accurate measure of the susceptibility, and the in-phase component of conductive response, if you have any kind of reasonable conductivity or high conductivity in the soil, the in-phase component of conductive response will mask the in-phase component of susceptibility response.
Barry?
Yeah,
Barry?
this
is Jim.
Yeah, I'm here.
Okay, I just like to. I don't understand magnetic susceptibility myself, but I'm trying to learn. The new sensors that are coming out simultaneously both measure at the same time apparent conductivity and the in-phase response, which is related to the magnetic susceptibility. So I've been exploring it a little bit more in my own work with soils, and there is an implication for magnetic susceptibility. We have an area here in the Piedmont where the continents collided many years ago, and we have serpentine barrens, and they have a different ecological site community. They're very unproductive soils, and electromagnetic in-phase response was it's telling us something that wasn't told in the apparent conductivity. So And I guess this would apply to California as well. Coastal ranges in some areas like that. The other thing is that when I use the in-phase response in Montana, I picked up a utility line that wasn't picked up with my apparent conductivity. And then in Illinois, we picked up differences in waste that were deposited on mine spoil. So there is areas for exploration or understanding. I myself am learning, but I'm intrigued now because modern equipment, modern electromagnetic induction sensors allow both to be measured simultaneously. And for those in NRCS, if you're doing any archaeological sites or stuff like that, take a look at the in-phase response sometimes. You'll be surprised what it shows. Thank you.
Yeah, thanks, Jim. We have a comment from Barracuda in the Erie, too. And the comment is, if you can relate iron content of a soil with productivity, magnetic susceptibility measurement will help. So that's interesting. Another thing I was kind of wondering about, I've come across some literature where the U.S. Army Corps of Engineers have used magnetic susceptibility measurement devices. Probes. I'm not sure exactly how they work, but to make direct magnetic susceptibility measurements of soil, and then use this to make determinations of whether the soil is hydric or non-hydric, which I guess helps delineate the presence or absence of wetland soils. So I'm just kind of wondering, can EMI be used in place of magnetic susceptibility meters for this purpose, or not? Again, this is well beyond my expertise, but I've always kind of wondered about with EMI if there's some, with the magnetic susceptibility measurements that you can get, if there's some additional important agricultural information out there that we could glean from this.
Yeah, it's Rick here again. First, let me get back to a couple of things that Jim mentioned. Tough for me to remember three things in a row. I think I remember two of the things that you mentioned, Jim. With utilities, you're not measuring the susceptibility of the steel; you're measuring the conductivity. That, I think, if it's a long conductor, that should show up in apparent conductivity as well. All the better if you have in-phase data to confirm it. With mine spoils, magnetite has tended to be a heavy mineral used in slurry to separate out lighter coal from heavier waste. So when we dump out mine waste from coal mine, quite often we have magnetite that gets dumped out too, and that would be the reason for the susceptibility there. I'm sorry, I can't remember the first one you mentioned, but to get on to hydric soils, yes, susceptibility should be able to show you where iron in the soil is being oxidized somewhat from magnetite to hematite. Although, once again, your success at this is going to be limited to areas, perhaps wetlands, with inherently low conductivity. But if you had, say, salinity in this mix, the conductivity from the salinity would mask the more subtle in-phase effect of susceptibility. Yeah, that's what I can think of offhand.
Yeah, thanks, Rick. Looks like we've gotten some comments and questions from the audience. Maybe we'll go through those. Might mention it again for all of our presenters. Sometimes to avoid any kind of feedback problems, if you're not speaking, make sure to go ahead and turn your microphone off. But read a couple of things from Larissa. Iron deposit coloring of the alluvial horizons of soils can be an indicator of poor productivity. Larissa, do you want to mention anything else about that? Or?
Yeah, I was kind of started thinking along those lines. If probably magnetic susceptibility would be different if iron is in like reduced state versus like in hydric soil. I mean, in hydric soil when it's oxidized and when it's like in spotted soil. I was asked Greek if it's gonna change anything. And on those soils, salinity is not a problem. There's probably they're non-saline. Iron would have a big effect, isn't it? Rick?
Okay. No, Rick,
Barry, I
here.
Yeah, I don't know. My comment gets there
Barry?
twice. I don't know why.
I'm sorry. I somehow I guess that was a question to Larissa. I didn't hear my name really at the end of that.
Okay.
I guess
That's okay.
Yeah, if you have acidity that is giving you that rusty color, or basically depletion of carbon in soil and other related chemistry that would indicate low nutrient content. Yeah, susceptibility could help delineate that effect. Basically, magnetite for non-magnetic iron minerals could be useful.
Okay, let's maybe move on. We've got a couple of questions here. One is from John Tainter. He says, outside of a research setting, in your experience, what has been the best means to approach a client to conduct these surveys? Not sure, Slava, would you like to maybe take a stab at this first, and we can maybe try to go on to some of the other presenters, maybe see what they think?
Well, there are several groups that actually doing this type of work for living. There is a variety of markets available, and agriculture is just one of markets. Somebody already mentioned archaeology, and we're looking at some of solutions for land reclamation. It's also quite a hot discussion topic here in Canada. And private companies, they have different strategies. Some of them collect proximal sensing data and then targeted sampling and make their decisions based on these components only. Some would also involve remote sensing or alternative data sources, both bare soil imagery and crop. We still need to remember that crop is the best soil sensor when it comes to agriculture, and whatever is happening with plant during growing, different growing stages is a direct reflectance of what's actually happening within soil. And also there is this approach of 3D mapping. In that situation, we have some sensors that non-invasive or less costly to operate. We can do high-density mapping and then identify specific locations where soil does look different in different parts of the area of study, and then go with another sensor that would be either hyperspectral or mechanical or profiler, and get measurements in those specific locations across the site. And then in the same locations, so we can do ground truthing, basically take some samples, do core scanning, sensor-based core scanning, or just break core into pieces and do traditional wet chemistry work on them and find out what it is. And then it's one of analytic solutions used. So there are different techniques for locating samples and different techniques for relating traditional measurements to actually sensor measurement. If we're talking about hyperspectral, we would be probably looking at component analysis and some maybe even fuzzy logic involved, and define what the relations for a given site, and then apply that model to high density data so that we can generate three-dimensional look of the field. And on the projects relating to irrigation, we also bring time as one of parameters, so it's not even three-dimensional, it's four-dimensional map of soil when we see how soil water changes from location to location, from different depths, and through time of growing season.
Thank you, Slava. I also have a question from David Redman of Sensors and Software. And I'll direct this, it's a GPR question, so I'll direct it to Jim Doolittle. And the question is, are there any GPR technology improvements that you think are important for soil characterization applications? Jim, you want to try to take that one?
Sure. Hi, David. Say hello to Peter for me. I'm intrigued with the processing capabilities. Computer processing seems to be the key to modern interpretations. I can remember early on in my career getting that ideal profile down in Florida. Everything was just right antenna, right setting. It looked beautiful. I don't think I can improve on it. My problem often comes into high loss mediums where I'm trying to push the envelope, go a little deeper or get a little bit better resolution. And I think computer processing and the analysis of the raw radar record is very important today. We can bring out more, and I'm hoping to see greater advances made there. Other than that, I'm quite satisfied with the modern systems. I feel like they're very, the old strip charts. Now we have it's displayed, it's digital. There's been a lot of advancement, especially in the 90s. And now I think that the big thing is computer processing, making better models to interpret our data. It's still an area of active research and development. But at the other side of it, we have 17 radar operators in NRCS. They have soil science backgrounds, and they aren't geophysicists. So we have to keep this simple that we can use, and that'll come with time. Thank you.
Okay.
This is Steven. If I could just jump in for a second, I was wondering if Jim or anyone else could follow up on that question a little bit to talk about some of the new advantage in multi-frequency instrumentation and multi-channel radars, if they're aware of any of that.
I'm unfamiliar with that, Stephen. Multi-channel, we use fixed, GSSI antennas. They have a fixed frequency. I don't know of any apparent advantage right now. I'm not aware of it. There could be. But that's another area of application for sure. Maybe in your Stephen, in your work out in at Stanford, maybe you could relate this or to modeling or facies analysis.
Sure, I could. I didn't mean to jump in on the speakers, but I could say that there are a lot of advancements these days, especially for shallow imaging of soils. People are interested in very detailed kind of assessments of what's going on. Some of the new multi-channel systems allow you to collect data very quickly. So it's like having, they have systems now with 64 or more antennas that you can run all at once. So 3D Radar is one of the companies that's putting some of those out. In our own work here at Clemson, we've been looking at infiltration, detailed infiltration mapping with radar, and we've set up automated systems with sensors and software SPIDAR systems. So that's kind of automated thing where it'll run and watch infiltration very quickly in detail. In the time scale of repeat 3D imaging of minutes. There's also a lot of work that's been going on with things like monostatic antennas and horn antennas. For example, Sebastian Lambo over in Europe has been doing a lot of work with that to mount those on tractors and things so that you could actually drive around and map fields pretty effectively. So that's some of the things I'm aware of. Ryan North just posted up a comment I'll release to everybody saying he's been using his 3D radar geoscope system for high density mapping of large areas. The system is 2.1 meters wide with 25 channels at 7.5 centimeter spacing between the channels. It's a continuous wave step frequency GPR. And that I think that's one of the exciting things that's coming down the line for people interested in detailed mapping with GPR are these multi-channel, ultra-wideband systems that were originally developed for things like landmine detection and utilities detection. So sorry to step in, but I'll release it back to the speakers.
Thanks, Stephen. I have a question. This is kind of something we hear about in the news a lot, and maybe direct this towards to Slava. And this is regarding drones. Okay, in the future, do you think that the unmanned aerial vehicles, or drones, can potentially provide a viable sensor platforms for obtaining geophysical measurements? Taking into account what are going to be public safety considerations and privacy issues that still have to be worked out, and what might be some of the advantages of using drones as platforms for geophysical sensors, advantages in terms maybe field accessibility, or what some of their limitations, load capacities. Any thoughts on where we might be going with the use of drones in agriculture, particularly with regard to using them as sensor platforms, geophysical sensor platforms?
Yes, Barry, this is actually a good question, and like when we work on new area, we use both drone and sensors, and partially because for the same reason that I just mentioned in the previous response, that we want to see how a crop performs in different parts of the field, and whether that performance is in agreement with what we see in the soil. The drone payload like the reason we are using it for optical exploration, because yes, we have a relatively lightweight cameras that can be in operation, and we have an optical reservation which has a lot of appeal, both analytical and also qualitative, that when you're just looking at pictures you have appreciation of what spatial variability across a given landscape. But also, like traditionally with piloted aircraft, there have been use of gamma ray sensors and EMI sensors and so on. So perhaps in the future, with relatively medium-sized drones, so those sensors also could be explored. Like the benefits of using aviation is again accessibility is one of them. If it's way too wet, or if it's area like marsh or peaks or some places where you just don't have access to that area, that would be a good opportunity. But also in terms of coverage, like when we talk about a remote sensing platform and can go all the way between satellites to drone, we can probably at less of cost to have bigger coverage than if we use suite of sensors. So maybe future application will go the direction that for large area exploration we are going to rely on aerial and satellite imagery to have a big picture, and then have specific locations where we go with sensors and use it more like a calibration, a case study, and then see how far we can extrapolate those findings.
Thanks, Love. Does anybody else have anything to add on this topic on the potential future use of drones?
Just one that I just remembered, thermal imaging is one of potential applications that have a lot of appeal.
Hey, I have a next question. This is going to be directed for both Rick Taylor and Larissa Golovko. And this is something I've kind of wondered about a lot, and that is soil electrical conductivity itself is temperature dependent. When using resistivity or EMI methods for monitoring purposes, say for water content, nutrient concentration, salinity, etc., over time, via electrical conductivity measurements, how does one compensate for these daily or seasonal soil temperature effects? So maybe start with Larissa, and then after that, Rick, if you'd kind of like to address your thoughts on that issue.
Okay. Well, temperature does affect resistivity, but I would say the effect of any properties go on exponential, and it's basically depending where are you on that curve you are. And usually in temperature-wise, if you're measuring during, say, summer, when it's warm, like soil temperature is relatively warm, and it doesn't, if it changes 5 degrees from, I would say, I don't know, like say 15 to 20 Celsius, it doesn't affect it much unless you're going on the other end where it's freezing temperature. And so changing water content through the 0 Celsius would affect temperature, and close to the 0. Temperature would have an effect. But I mean, in general application, temperature wouldn't have that much effect. I mean, during growing season, I probably didn't make myself clear on that.
Rick, do you have any thoughts on that? Or is this,
Sure.
is this even a...
Yeah, Barry, absolutely. I'd love to address this. Yeah, just further to what you mentioned, Larissa, when soil goes through frost point, freeze thaw, conductivity changes over a couple of degrees through frost. Conductivity changes by roughly an order of magnitude. So if you had 30 millisiemens per meter soil unfrozen, you would expect about 3 millisiemens per meter response after freezing. So that's now, of course, bear in mind clay-rich soils will resist freezing to quite an extent because they tend to hang on to a fair bit of dissolved solids in the pore fluid, which lowers their freezing point. I guess just in general, Stephen, would you please throw up my my presentation? There's a slide in it that I'd like to refer to here.
Sure, I'm bringing it up now. Just one second. Do you want your short presentation?
No, the long one, please.
Hey, there you go, Rick.
Okay. Now, people, please understand, I really don't know anything about this because all we do is build instruments. I don't actually go out and take any measurements of significance in the field. So I tend to look at what people do with instrumentation and base my knowledge on that. Fortunately, there are some just great researchers to look at their work, and Roger. I have high regard for Roger Eigenberg and his group in Nebraska. Here on this slide is a whole series of apparent conductivities. These orange lines are apparent conductivities measured from end of March through to end of November in test corn plot that they have at Clay Center, Nebraska. I'm sure Roger is aware of how much conductivity changes with temperature. The way I guess try to make sure that this wasn't a variable that really I had to be worried about, or if it has a significant effect relative to other effects, you could implant some thermometers at reference points and look at how warm the soil is versus how conductive the soil is at those reference points that you go back to again and again and again. But Roger and his group measured conductivity as nutrient was applied, nitrate was applied to the corn plot, and they also measured the degree of saturation of this corn plot. The really major effects in conductivity that they found had to do with saturation level and also nitrate dissolved in the pore fluid. Here we have conductivity drop a lot when the soil got dry, but conductivity didn't recover even when the soil got moist again, because the rapidly growing corn was stripping out the nitrate to build its fiber. So with this paper back from 2006, where was it now? It was in Soil Science Society of America journal. 2006, I expected that Roger's group had some discussion of the temperature effect on conductivity, but what I remember from that paper is that the temperature effect wasn't nearly as significant as the moisture and the dissolved solid effect of conductivity.
Oh, thanks, Rick. Yeah, I guess, what I'm seeing is we have a lot of really good, comments that are coming from people as we go through some of these questions. Hopefully we can kind of capture these, and this can all be a part of the record of the webinar, because just looking through some of them, provide a lot of insight. I guess next we have a time for a few more questions, and like the next one I would like to address to Jim Doolittle. And Jim, you've developed these GPR soil suitability maps for every state in the U.S. And I find these to be extremely valuable information, especially for anybody that plans to carry out a GPR survey. I'm wondering if you could maybe take a little bit of time to discuss what the factors and criteria you used that went into doing these GPR soil suitability assessments.
Okay, Barry. We have different scales of mapping, and we had to have properties that were consistent. When soil samples come into the National Soil Survey Laboratory for analysis, maybe they run it's sort of like a quick check, and they might check for conductivity. If it doesn't exceed a certain level, they don't run it. Yeah, if we can go to that map backwards. And so what we did, we prepared a map of electrical conductivity in the United States, and that was our first attempt. We said, hey, this is what we want to show. But what we got was there was this threshold level. So all the they only ran conductivity when it got to be really conductive. So the whole United States came up conductive. What we looked at is the depth of penetration is dependent upon moisture, clay, and soluble salt contents. There's too much temporal and spatial variability of soil moisture, so that unfortunately was not included in this map. So we assume that this rating that we see here is for well-drained soils. We do have texture, and that's probably what in the eastern half of the United States is basically a textural map. In the western portion of the United States, we included, well, it's included everywhere, but salinity, sodium absorption ratio, calcium carbonate, and calcium sulfate content. We improved it in 2006 by including cation exchange capacities of those low activity clays in the southeast. That was incorporated into it. It's a broad brush attempt. It shows general conditions, but the actual suitability will depend on your application, the target you're looking for, what equipment you have, but this can give you a general view, and that's what it should be taken as, a general view of the United States and where and in what regions radar is best suited. Here in the Northeast, you can see it's all green. And if we have a lot of sandy soils up there in New England, coarse texture soils. You can see the sand hills of Nebraska, the Anoka sand plains of Minnesota, the southern peninsula of Michigan, the western side of it. But then you also see areas of clayey soils, and then you see in the west, the basin and range, you see the high percentage of soils that have salts in them. So it's a general broad brush stroke attempt to show general suitability of soils to radar. It's not perfect. It's still being developed. We have more data coming in. We're hoping to have a revision in the next couple of years based on, we're going through a process called soil data joins, and this map looks pretty good, but on some of the state maps what you'll see is political boundaries, and that's the age of the soil survey, the amount of information that was available. So you will see political boundaries show up. On this one, what bothers me the most is in southwestern Kansas, we got a square there, and soils don't follow those straight lines, political boundaries do, and so probably what we have is county boundaries there. Okay. Thank you, Barry.
I guess a couple questions, Jim. So you, through the NRCS website, you can get the each individual state, the soil suitability map. Is that correct at this point?
That's correct.
And also, do you have the capability of, I mean, say you know your location in terms of, whatever, latitude and longitude. Is there a way of entering that, precise location in and coming back with kind of what the soil suitability is for that, rather than trying to pick it off on the map? Yeah.
Yes.
Capabilities. Oh, you do.
Yes. Bob Dobos and Sharon Waltman, both soil scientists at the National Soil Survey Center, they're our programmer and our geospatial specialists. And there are ways to import it into the web soil survey, so if you have a soil map, the classification can go into it. But I don't know how that's done myself. I wasn't involved in that portion of it, but we just had a request from a company in California that wanted it imported into their GIS, and there's a way of doing that. Unfortunately, I don't know that way.
Okay. Well, thank you. I guess, Stephen, it's like it's 4:30 now, so we're kind of at the end of the scheduled time for the webinar. Just thinking, what are your thoughts? Should we go ahead and stop at this point? We still have like our Ag Geophysics website open that people can go in and still direct questions to the presenters and get a response back, via email. Just kind of, I don't know what we think we should do at this point. Go ahead and just continue the webinar, or continue it for a few more questions, or I'm not sure. I'm just open for suggestions.
Okay, well, this is Stephen, and the questions have kind of been dying down a little bit. So if anyone has any pressing question to bring up right now, go ahead and enter it, maybe last minute question, or if anyone has any comments about the webinar in general and things you think we could improve or do differently, please also enter those in. Otherwise, I think we should probably wrap it up right away. I would like to thank everyone for attending. Particularly, we haven't shown you all the attendees list, so you can all see how many people are actually logged in. But we've had a really big attendance for this, and we really appreciate everybody who wanted to participate and hear a little bit about it. Barry, I'll let you thank the speakers, but I definitely also appreciate all they've put into this as well.
Yes, I definitely want to thank the speakers that provide some really good presentations, both these overview presentations and also the more extended presentations that you can view at the website. I think what they've done is really helped us get off to a really good start. Likewise, I want to express my appreciation to Stephen, the co-chair, who's really got this set up in Adobe Connect. I think it's a learning process for us, and I think it went pretty well the first time. And also with our organizing committee, without their help, we wouldn't have been able to get all this done. So we really look forward to putting together the next webinar, and we'd certainly like to get the input from the participants here on maybe what is the topic of the greatest interest for you. And we'll get this information, we can go ahead and get started in lining up speakers for that particular topic, whatever it might be, water content mapping, nutrient monitoring, forestry applications. You know, the list goes on and on. So we definitely appreciate hearing back from you on what you thought went right, and you know, where we could use some improvement. So I think that's really about all I have. So I guess again, thank everybody for their participation, and I guess we can go ahead and log out.
Great, thanks
Anything else,
everybody.
anybody?
Thank you, Barry. Thank you, everyone.
Good. Thanks. And we'll get this webinar hopefully loaded up, recorded webinar loaded up later this week for those that might want to go back and look at this again, or if you know colleagues that couldn't participate today, they can hopefully go and you know, view the webinar themselves. Thanks again, everybody. Bye-bye.
Thank you.
Thank you.
Thanks. Bye.
Bye.